Okay, then for folks in person, there that is in the collaborative notes doc. So everyone should be able to access that now. Yeah, no, we're a little behind, so we might as well just get started. With that, before we get into this, I'm excited to introduce both myself, Keenan Gans, and Chris Battisto. We both run the Interoperability and Information Technology Cluster here for ESIP. You may have been seeing emails from me about the talks that we've had going on lately. Today, our session is Earth Data Connections, focusing on technologies that enable interoperability in the Earth data science sphere. Our talks today include first one from myself about using XBatcher for deep learning workflows, another from Chris on the X-array data tree data structure, and then we'll finish off with a demo from Rajat Shinde about the cloud optimized point cloud format, which is like a cloud optimized way of working with LiDAR data. So with that, before I get too far into this, and I'll make sure that I'm sharing the screen here for everyone online, folks in the room, are we all able to look at Colab? Like, are we all able to see that? Cool. And I hit the wrong button, so I'm going to fix that real fast. Okay. Okay, so I guess we can keep going with it then. All right, well, let's go ahead and get into it then. So one thing that I end up having to do a lot in my work when I do any kind of deep learning stuff with geoscience data is we often start with data in a contiguous array, like n-dimensional data structure. Think like an X-array or a NumPy array, so on and so forth. However, when we actually go to train a deep learning model, we operate on small pieces of the data. And so there's kind of a slicing and reassembling step that goes into that. XBatcher is a project that was started a few years ago by others in this community to take an X-ray data structure and then cut it into pieces that we can then efficiently feed into a model. It provides a nice sort of high-level API to accomplish that based off whatever windowing dimensions you want. You can specify overlaps. It's a really convenient structure. However, that's kind of this first step here of starting with input tensors. You can pass that to your model, and then that will generate output tensors. One thing that may be kind of missing in this workflow, though, is you may want to take the model output and reassemble that back into a labeled X-array data structure. That part can be a little bit more challenging because there aren't really functions to make that happen. So this is a demo of some proposed changes that might be going to XBatcher to make that a little bit easier. I'll also be showing some new features that I've also made a pull request on XBatcher for to enable filtering and resampling for these workflows. So with that, we can go ahead and get into it. The way I've set this up is the first thing to do is you actually have to clone the Git repo associated with this. So in our first cell here, you'll see like this command will be commented out like that. Make sure you uncomment it and run it. So you should be able to do that, and it's going to error out on me because I already cloned the repo, but you should see that actually clone and then copy some extra code kind of into your project here on Colab. We'll have to do some extra installs as well. Again, I've already done this, but shouldn't take more than just like a few seconds. The whole workflow that we're going to do here is we're going to train an autoencoder on terrain data. And so the first step for us is to bring like a granule of elevation data into the project. We're going to start also with just like imports. This is all just like setup. This is meant to be a very interactive session, by the way. So if I'm like going too fast or if you have questions or anything like that, please do stop me. Yeah, go ahead.
Is it possible to just describe like for the newbie like why you have to break it into like pieces by itself?
Yeah. So that's off. Oh my goodness.
Or is that too? If it's too long, don't worry about it.
Well, it's mainly because like if you have like imagine you have like a really, really big image, like 5,000 by 5,000 pixels. Maybe that's not huge for some people in this room, but it's large to me. And then if that goes into a model that is then going to do linear algebra operations that make much, much larger arrays than that.
It's because of linear algebra.
Yeah. And it's also because oftentimes the kind of task we want to accomplish with a model only really makes sense on like chips of an image, right? Like if I want to do, like the example I'm showing here is like a land cover classification. Like, yeah, you could do that in one shot across the entire image, but it's generally a lot easier to operate on small chips. There's also an advantage there of, like, say I want to do land cover classification, but I want to ignore a certain geographic region. Or I'm pulling data from a sensor, and I know I have sensor failures in there, and I want to exclude those pixels from the workflow. In that case, then, you know, it's much more natural to account for all those things working in these like small chips. Okay. So we should have everything imported. We're going to be pulling some data from over the lovely Olympic Peninsula here in Washington State. You may notice I'm using Planetary Computer to pull this data in. That choice is just arbitrary. It's in my opinion, the fastest way to just get data into a notebook so all of you can like play with data instead of having to set up like Earth access credentials and all that. However, you could just as well do this with Earth access or whatever open source collection you prefer.
So Planetary Computer stack thing still exists, and all the data sets exist, just the hub went away, or so. I like people said, oh, the Planetary Computer went away.
Yeah, so the question for people online was, you may have seen some news earlier, I think it was either this year or last year, that Planetary Computer was like shutting down. That was just their compute hub that they got rid of. The data is all still there, and you can query it as we're doing right here. So I just drew like an arbitrary box, this blue box on the peninsula that happens to intersect with 6 granules from the NASA DEM. We don't need a ton of data for this particular demo, but you can, you could do this with more granules or fewer. We're just going to pick one. So we can do that, and we can pull it in. So we wait just a second. One note here is that we're rescaling this from 0 to 1. That's really just like a tiny detail related to this particular workflow. It's kind of separate from the whole like Xpatcher approach that we're going to show here. So you can see like I have all those data in memory, and I can do a plot. And there we are. This is maybe like the south central part of like the Olympic Range or something like that. We have lots of mountainous terrain, as well as through here, that's like a water body and Hood Canal, and then some lower kind of like valley features through here. So now we get into the first step of what Xpatcher enables, which is taking a large image. In this case, we have a 3600 by 3600 image, and I want to cut it into pieces that are 32 by 32 pixels in size. This is very easy to set up. This is the entire, piece of code that actually sets up that structure for you. All we have to do is specify what dimensions we want in the X and Y axes, as well as the overlap. Another feature that we may want to have is we may want to filter out certain pieces of terrain. Maybe the particular science question we're interested in, we want to exclude low elevation areas. And so a new feature that I propose for Xpatcher is to allow the user to specify a function that takes the data set we're slicing and indices that are like associated with a particular slice, and then return a Boolean just to say whether or not that patch is accepted into the data set. This is a very simple example of how that would work. And so we can run this. We should see some output here showing that we have about 10,000 patches after filtering. So even though we've discarded a little bit of data, we still have quite a bit to work with here. And just to visualize what's going on with this filtering step, this below image is just painting pixels with a value of 1 where a patch is accepted, and then pixels of 0 where a patch is not accepted. And so you can see here, comparing with the original elevation image, that all this like lowland area through here, that's been excluded. So that's not going to be a part of model training. There's another small piece of work we have to do to actually like link the data together. For a deep learning project, really what you need is just a way of mapping an index to a particular batch of data that, well, really it's an example, and then those get, besides the point. You just need to map like indices to data. And so there's a little bit of work we have to do here to actually set that up. And then just for fun, we're also going to set up a validation data set here. This is just kind of taking all the code that we've done so far, wrapping it up in a function, and then applying it to a separate granule. This is helpful to make sure that we don't have overfitting when it comes to running the model.
So this is just sort of a detail, but I see you're using stack, you're not using ODC stack. Is that because of any particular reason?
No particular reason. This is adapted from some code I wrote some time ago, so it's just what I had on hand. And you can see that this is all like relatively efficient. This like filtering step doesn't add a whole lot of computational overhead. You know, we're able to go through this entire like pull data into memory, apply windowing, and apply filtering to it, and we can do that on 2 granules in under 10 seconds. So that's really not bad. Well, okay, 15 seconds, but you get the idea. So we're going to set up an autoencoder for this, and this is a really interesting architecture in that what we're doing here is data compression. So we're taking a 32 by 32 image patch, compressing it down into a vector with 128 elements, and then using that compressed version to reconstruct the original output. One way you can think about this is you're training the model to throw out essentially 90% of the information that goes in, and then reconstruct what went in the beginning. You might be asking yourself, why are you just reconstructing your data? Like, what's the point? Really, we're interested in using the kind of latent space in this data for like a downstream application, for something like classification and so on. Again, the use case here isn't particularly important. This is more to show what Xbatcher can let us do for these kinds of workflows. The autoencoder that I have implemented here, that is just like in a sidecar py file. That's why we had to pull a Git repo in from the start. But that's there if you want to jump into it. We'll make sure that all the shapes work out. This is just going to run that model and make sure that the shapes of the input and the output tensors make sense. And then we'll do a bit of training here. So this will think for a second. This will also store the resulting model kind of as a checkpoint right next to you in the directory. We don't need to train this model for all that long. In fact, we're only going to do, I think it's set to just do like 10 epochs. Yeah. And you'll see that that's actually enough to get like pretty meaningful results. So we can all just watch this blue bar go up for a little bit. I know I'm going pretty speedy, but are there any other questions I can answer kind of just while we're waiting for this to go?
So this is on a GPU?
It depends on what your Colab runtime is. I think the notebook might be set to use a GPU.
Yes, it's GPU available true, used true.
All right, sounds like we're on GPU then. Cool. Really, this example is small enough you could run it on a CPU like without that much problem. Yeah, just to reiterate, kind of the whole game here is we started with a big image, we cut it into pieces, and now we're training a model on it. The next step then is to take the output chips from this model and then reconstruct that into the labeled X-array object we started with. Because once arrays come out of a deep learning model, they're just arrays. They lose all that labeled useful information that we have with X-array. Which means that, this is good timing, right as this is finishing. So we'll do one last test on that data loader, and it's done. So this means then that if we lose all that information, I'm going to show a couple examples. So this is like kind of what that model is doing. You can see it's starting with an original patch of terrain data and then building a reconstruction. Note that in that process, the model throws out 90% of the information that is in, well, it compresses it, down to 10% of the original amount of data that's there, and still able to do a pretty nice job reconstructing the outputs. That's kind of neat. But if I wanted to take these reconstructions then, these little chips, and stitch them back together into a data set, that can be quite painful. This is perhaps the old way you might approach doing this. Manually making an array of zeros, iterating over each piece, passing that to the model. There's a lot of like +1s and just really nasty indexing here. But it works. I can like run this and that for loop will cruise for a little bit. You'll notice also that this is a little bit slower than what I'm about to show you. It's just taking its sweet old time. Yeah, it's rough. Again, like because, so this is really the kind of motivation for this whole talk, though, is that if you want to assemble patches manually, you have to do that. But we have this batch generator object that already knows a lot about, like, what were the input dimensions? How do they map onto the original data set? And so we can use all that data that's in that model to essentially do this same nasty nested for loop thing, but with a much, much cleaner API. So I can just like justify to you that the reconstruction works. You'll notice because we excluded all that lowland data through there, the model still like operated on that, and weird things happen. You know, neural networks don't extrapolate. What else is new, right? So there's some other examples in here. This is really like the function of kind of how I'm currently approaching taking tensors and reassembling them into an output. We don't really have to read that. That's all there if you want to look at it. But the new way of doing this then is I can make a new batch generator for just a portion of this data that I want to reassemble into output. And instead you can just call this function. And here we're actually doing a particular, there's a bit of a subtle piece here, where we started with an initial array, and I know thinking about array dimensions at 8:30 in the morning is like kind of hard, but like bear with me. We started with a 32 by 32 array, and in the model itself, we compressed it down to a single array with one dimension of 128 features. So another neat thing that Xbatcher lets us do is you can modify the dimensionality of your input data. You can add new dimensions, modify the dimension size, and we can account for that. So in this case then, I can go through this process of assembling output, and now I have a new channel axis. And that is just assembled alongside the original geographic coordinates that were in the array. So if for whatever reason you wanted to look at the particular values of your latent features, you could do that. You'll notice like I still have the original coordinates through here. We can also do that same approach I showed you earlier of just assembling the reconstructions to make the original data set. And I can show that here. Again, there's no nasty for loops here. It's just call a function. And then just like one last example here of like what's kind of interesting about training these models is you'll notice that in this one-to-one plot of the reconstruction versus the input data, because we excluded stuff that was lower than the 25th percentile of the original data set, the model goes crazy when it gets data outside of that. And it has very odd behavior around there. So that was a very speedy demo. That is all I have to show you of how we can use Xbatcher to both filter and resample data for training, as well as use it to reassemble model output. That notebook is there if you'd like to tinker with this a little bit more. And do we have time for questions? Okay, yeah. So if there's any questions in the room, I'm happy to answer them. Yeah.
So Xbatcher can take.
Which one to give you?
Yeah, so the online folks can hear.
So Xbatcher, can it take more than 2 dimensions?
Yeah, so it can take arbitrary dimensions.
Yeah.
Like this is the choice of like the sizes and the numbers of dimensions we're working with here are totally arbitrary.
Yeah, okay.
You could do this with, you can make batches based off time and geographic coordinates. You could have it based off of channels. You could have it, however your data appears. If there's nothing online, then thanks everybody for your attention, and I can pass it off to Chris. Yeah. Oops. Where are we going? Here you are. Okay. So it's on extend.
Cool.
Right now. So I'm gonna move this over here.
All right, well, good morning, everyone. My name is Chris Battisto. I'm the current chair of the ESIP IT&I cluster. I want to thank you, Keenan, for helping co-chair this session. And today I'm going to basically tell you all about a open source story that has some very wide applications. In the IT&I cluster, we tend to show lots of different workflows. We like to show tools that are easy to use for users of all levels, particularly when dealing with geospatial data of several formats. And so today we're going to give a little bit of a demo that was kind of expanded on from some work at the SciPy conference last year, which is about X-ray data trees and some ways that you can access those using some efficient patterns rather than some old methods. And just like in the previous demo, you saw some of the old ways, I'll also do that here. So just a couple of things about me. I'm originally a meteorologist. I studied at Northern Illinois University. I also have a computer science background and over a decade of Python experience. I work in user needs. So basically that's publishing tutorials and user guides for lots of different NASA Earth data collections. And those, again, are typically Python. Python, most widely supported tool, typically with a lot of these programming utilities. Yes? Oh, goodness, yeah. Ah, okay. Let me switch the, yeah, you're probably all seeing my notes.
We're mostly just seeing your next slide. It's nothing too juicy that we're.
Right, yeah. How about this? We will just do it I wish I figured out Zoom, but let's just do it the old-fashioned way. Oh boy, where am I going? Bear with me here 1 second, please. Okay, perfect. All right, yep, sorry about that, thank you. Again, all these tutorials, I currently host a GitHub repository that has over 25 different Jupyter Notebook tutorials, several different Anaconda YAMLs as well. And these recommend workflows for all sorts of applications and user levels. Typically, the tool is kind of determined by the data format. With Earth data specifically, you have several different processing levels. I'll get into that a little bit later. But I have a few goals with this demo today. Always, I want to figure out ways to navigate these different data formats without headaches and to be able to open them, view their metadata and their structure in a way that I can more easily understand it. I wanted to approach this from a user perspective. This project is kind of curated by engineers. I'm not really an engineer, I'm just a developer. But what I wanted to do was learn about how they implemented it, think about some different ways to show it. This was created out of a need to improve a subsetting service, and so this might be something that if anybody here is thinking of creating a subsetting service or is currently working on it, might help you out with that. Another thing was for the last few years, I've known about something called JupyterLite, which is basically a serverless implementation using WebAssembly of running Jupyter Notebooks in the browser. It's really come a long way in the last few years, and so I'm excited to finally be able to have a working demo using that today. And then finally, sometimes the best way to learn about these things is by demonstration. So I'm hoping that if there are any bugs, then we can all learn from each other with that. So as I said, there's a lot of different access patterns in little time. You've got different processing patterns or different processing levels with a lot of Earth data. So that's typically level 1 through 4. As this data comes down from the satellite, sometimes you can preserve the tracks. Sometimes with the higher processing levels, you can organize them into an actual grid. But unfortunately, they have very big structural and metadata differences. And so the data format kind of reflects that. So you can have a Tropomi collection that looks completely different and structured than an OCO collection or a MERA collection, and so on and so forth. And so there are definitely multiple levels of difficulty, and that can result in Jupyter Notebooks, for example, that can be extremely lengthy or extremely efficient and dense. I've had several webinars where we just want to look at a simple hurricane scan from a level 2 data set, and it winds up where you have to go through all sorts of different patterns just to be able to look through the groups and dimensions. And so it's important to be able to choose your library wisely and to also make sure that you don't hard code anything. And even in this demo today, we kind of assume a couple of things with the collections that we're going to be using, but that's just something to keep in mind, and a reason why a lot of these different open source projects are so important. So I want to talk a little bit about hierarchical data formats. So you might have all heard of these. There's HDF. HDF is something that's been around longer than I've been alive. It's the underlying storage spec for the netcdf4 file format. So that's the .nc or the .nc4 extensions that you might have seen. netcdf4 is actually an API that's built on top of HDF. netcdf can get a little bit clunky with things sometimes, but it's got a lot of different metadata that is CF compliant. That's pretty useful for a lot of climate data sets. And so basically you combine data sets and groups. And so HDF files can contain groups and then subgroups of those, all with their own metadata. And they could be single or multidimensional. But it's basically sorted like a file system, and it's kind of isolated from each other. So you have to, if you wanted to, for example, compare one group to another, if there's a co-location you wanted to perform, you have to have code that traverses all of those. And if you're creating a subsetting service, even if you wanted to pick maybe one time slice or create a spatial subset, there's a lot of things that needed to be done. Lots of very manual, kind of low-level operations. And so I'll also show you what that used to look like before this project. And so that's basically a workflow here of what that kind of looks like. So you would use the netcdf4 Python library. It's a very robust library, has lots of different tools for working with the individual arrays. We typically use it over for Earth data tutorials, for level 1 and 2 tutorials. But what you have to essentially do is basically copy all of these groups, stick them into a new netcdf data set, which will hold all of those copied groups. You have to manually traverse them and recursively traverse them. And then you perform your subsetting, then you can save that and export it. And so if you are, for example, making a tool, you can imagine that you have a user interface. I just want one time slice. Maybe it could take some time, and that's really just because there's a lot of operations in here in code that allows for a flexibility of those collections. So that can be lots of different lines of code, and even if you're just trying to make a simple demo, it can be quite complicated. So out of this need came this open source collaboration through some folks that I work with, and also through some folks that are in just this open source geospatial community through Pan-GeoForge channels, for example. So basically, we had this open source collaboration with, you can see Eni Awawale, who I want to thank her very much for letting me use some figures and some code in this example. And so those folks over at NASA GESDISC, along with some work from some X-ray core developers and Tom Nicholas, were able to get this project working. And then it was merged into the main X-ray core channel last year. And so now you can see that you can access this, and there's extensive API documentation about it as well. So what an X-ray data tree tries to do is basically make it easier to interact with these HDF files. And it does that through inheritance. So it allows for these dimension and attribute inheritance. It also allows you to interact with the data files in a way that you can treat it almost like a relational data set. So you can see on the right there basically just how a data tree is structured. You can have data trees underneath data trees. You can have several different groups, but they all can inherit different properties, even though they all, for example, with the Simpsons example, they might have different ages or different genders and so on. The same thing is applicable for geospatial data. And they made a really good decision to put this in the X-ray tool because X-ray has lots of different things that you can do, calculating all sorts of statistics, regridding, using Dask for parallelization. It's very efficient, of course, if you know how to use that properly. But it runs all of that workflow in just a single line of code, essentially. You might still have to know the group names, but that's pretty much the least of your worries, and there's always methods you can use to extract those. But then it just turns into this line of code that you can see on the bottom right, where you just open up the data tree from a file, and then you can simply append any of those operations for calculating any sort of statistics that you want. So this is what it used to kind of look like. So you used to have to either use netcdf4 Python, or with open dataset, you would see a dataset that looks like this. And so it looks like it's empty. It looks like there's a problem. I don't see any data variables. I just see this time dimension. I know that this is 10 hours in this particular data file, but I don't really see anything else. And basically that's because I need to manually specify the groups when I open up these data sets. And so there's a keyword argument that you would put in here called group equals. And then, for example, if you're accessing a GPM iMerge granule from an OpenDAP server, you would put group equals grid, the string. You have to make sure that it's that you have the correct case as well. Those can be case sensitive. But with Open Data Tree, this is all you see when you do that. You actually see all the groups, you see all the variables, all the different coordinates and dimensions, and you can see how they're inherited throughout those collections. So I've highlighted in the bold, you can see the top /, which is the root group. Underneath that, you have this time dimension that is inherited through each group. And you can also see a couple of differences here, which is one of the reasons that HDF files and netcdf files in this fashion are kind of useful, is that sometimes some of those dimensions are out of order. You can see in this observed dimension, longitude is first, in the reanalysis one, latitude is first. So you can have some variance, but sometimes you need to have a time dimension through all of them, and you know that that is applicable for all of them, but sometimes time is limited to a coordinate, and so you have to manually go in there and add everything. So data trees are really great for that, but there are a couple of caveats right now. It's still a little bit early in its implementation. Ironically, HDF4 files and HDF5 and all the other variances of HDF files can't be opened explicitly. It works really well with netcdf4 files or the ZAR format. Right now, there is no open MF data tree function. So for example, if you wanted to open multiple data sets, you can concatenate them along a dimension. Right now, you can only load one data tree at a time. That kind of comes out of this need to create it for a subsetting service, as most users are exporting one file at a time. It cannot access remote data files. So for example, if you were using the Earth Axis library, which uses the fsspec library, which basically mounts that remote file system in your environment, it doesn't have support for that. So in the example file that we have, we just stick that in the GitHub repository. And then you still need to know the group names, and so you'll see how I call those later in the demo. So I think I hope I don't go a little bit over time, but basically for this demonstration, it's going to be a little bit different, and it's something that I'm excited that I'll be able to show you all today. I know we have a few educators in the room who might be interested in showing Jupyter Notebooks. This is a very interesting implementation of it because it basically runs in your browser, and it's kind of isolated to your browser. So it uses something called JupyterLite, which uses WebAssembly. And so you can basically run this notebook anywhere without the internet, as long as you have it loaded, of course. In this case, you're not going to need any login. It's not going to connect to any sort of remote compute instance. It's literally just going to run in your browser. And if you're running a 32-bit browser, you might have some performance issues, but that's basically how that works. And so when you close it, you might have some of your extra code, for example, saved to your output, but it depends on your cache settings with your browser. It uses the Zeus Python kernel, which uses something called emscriptin or mscriptin. This is essentially a LLVM, a low-level virtual machine, which allows you to install these libraries before you compile the JupyterLite notebook from channels like Conda Forge. So before, with JupyterLite, you have this repository that you interact with something called micropip. And so basically it's a collection of all these different libraries that users or developers basically have to manually curate in order to get JupyterLite to work with some of these libraries. So there was a bit of a delay in getting things like Xarray and so on and so forth. So that's what we have here, and that's how I was able to install the netcdf4 library in here. With these, you can deploy them over GitHub pages. There's a template in the Jupyter Lite server. You can simply, in GitHub, just duplicate that template and then edit it yourself. I've also linked to the GitHub repository in the shared document if you would like to access that. And so what we're going to do is look at that sample precipitation.nc4 file, which contains both a Mera group and then a GPM iMerge group, and I'm going to show basically what that looks like in real time. The only caveats with the Jupyter Lite Notebook is that it cannot connect to external internet like file systems and things like that. It's limited with browser security and cross-origin resource sharing. You'll notice that you can pretty much only do the things that I do in the notebook. If you tried to open up an OpenDAP data set with Xarray, you'll get errors. There's lots of different libraries that have just variance in functionality. So that is just something to keep in mind. But it does allow for that flexibility. You can run this notebook from your phone if you wanted to. And fortunately, no experience is necessary for this demo. So let's go ahead and get started with that. So I've linked to the demo in the ESIP schedule for this. So it looks like I'm going to have to go and navigate there. And I've just got it linked under the speakers section. All you have to do is click demo. And you can see that it's loading. It's basically just compiling itself inside your browser. And without any login, without any external compute, I'm now able to run this Jupyter Lite notebook from within my browser. And you can see that it's a typical Jupyter Lab setup. You've got your file explorer on the left. You've got your interface on the right. I haven't messed around with a lot of other things in here, but you can see that it's got that XPython 3.13 kernel. I've got the actual live demo here. I've got 2 copies of it. I was originally going to show how to kind of do it live, but I kind of don't have my notes like I thought I was going to have it set up. So we're just going to do this data tree demo here. So if I double click that, that's going to open up on the right side. And then for anybody who's not familiar with Jupyter Notebook, this is essentially what it looks like. It just combines Markdown with Python code. And we don't have to do any sort of installations with anything. All we have to do is click the cells in order. In order to run a cell, you can either click inside of it and press Shift-Enter, or there's a play button at the top here. So what we're going to do is just show the new way of doing things and then the old way of doing things. So the first thing we're going to do is load our libraries. And when I run this, again, it's running from completely inside your browser. After that, what we can do is we can use the open data tree function. And so you can see I've got that netcdf4 file on the left. It's a very small netcdf4 file. You can feel free to download it. And then I just wanted to go ahead and run this, and so then we can see what it looks like. And it's basically the same thing that you saw in the slides, where we've got that time dimension. This contains 10 hours of Mera and GPM data, and it's going to show a scan of Hurricane Ida. After that, all we have to do is perform our subsetting. And so in this case, I just want to calculate a spatial average over those 10 hours. This data has a precipitation rate in millimeters per hour for the GPM group, that is. And so you can see that when I run this mean, it reduces that time dimension because we did that over that dimension by specifying it with mean. But you could see that I've got all of those different attributes and dimensions inherited throughout each of these groups. And that's really useful because now all I have to do is just call the group and then the variable by using a simple string and then the built-in plotting methods. And so you can see I've got this new subsetted variable called dt_mean. And then what you do is you can navigate through the different groups kind of like you would on a file system. So I've got the observed group and then my precipitation variable. And so this little matplotlib is building the font cache is something you'll see every time you run this, specifically in Jupyter Lite. But this is some of our 10-hour average precip of Hurricane Ida over the Gulf of. Yes, exactly. And so with the old way of doing things, basically we show how to do that with netcdf4 Python. Again, it's a very low-level library. It's very easy to interact with the arrays. But you can see already here we have to basically create those two new boxes. So we open up our original netcdf4 data set, and then we have to create that new data file. And what this does is it basically opens up that data file, and then it kind of writes to it, and then we have to manually close it. So we're going to run that first, and then on the left side, you'll actually see that, that new file loaded, but you can see it's got 0 bytes. Then after that, we have to do some work. So I don't know if you've all seen Spaceballs at the beginning where the ship just keeps going and going and going. It feels like it's never going to stop. That's kind of how it felt like when I was first trying to get this to work. So we've got our first function that copies all of those dimensions. You can see that we've got logic in there to skip the time dimension because we know that that time dimension is in that root group. We have to make sure that we inherit that. We also have to make sure that it has the correct units since time is dimensionless. After that, we copy our variables. You can see again that we've got a little bit of hard coding in here. We know that we've got time. We know that we've got latitude and longitude in those coordinates. So we have to manually traverse through everything and copy it into, new var, new dim, for example. We have to do extra testing for that time dimension again. And then finally, for the recursive copy, this basically just performs that actual copying, and then it does the actual the mean in there, the spatial mean. So when we run this, it's actually quite fast. But you can imagine that if you're creating a code base with a subsetting service that has to deal with loads of different HDF files from lots of different collections, you're putting in a lot of time to make sure that things are as minimally hard-coded as possible. But then finally, I've had enough of that. I just want to open it like a data tree again, just so that I can see the structure of that. And then we can finally call it, just like we did before, with that observed precipitation and plot it.
Is that actually the way you used to do it, or did you do that first?
It was, no. This is, in the original presentation for SciPy, they don't really show the actual code that they used, but they talk about how they have to flatten these arrays. There's all sorts of operations that make those subsetting more or less efficient than others. But I've never really seen what some of those subsetting services use, but you can certainly imagine that it was quite long. And nobody really wants to create just a GPM subsetter or just a MERA subsetter. And so that's basically what this looks like. So just going back to the slides. I just wanted to give some acknowledgments. I wanted to thanks to my colleague Annie Awawale for providing those example code and some of those figures, and also for helping create this library. I also want to thank Keenan for helping putting together this session, and I want to thank you all for joining today. And with that, I think I know we're a few minutes over, so I think I've got about 5 minutes for questions, maybe.
Yeah, Rajat also,
Okay.
he dropped off the meeting and he sent me an email saying he's having connection issues.
Oh, okay, that's too bad. Okay.
Ask as many questions as you want.
Yeah.
So what was the process for packaging up that stuff so it'll run in the browser like the netcdf4 file?
Yeah, I could actually show that. So it's really simple. It uses GitHub Actions, and all of those things are done automatically.
Chris, could you repeat the question?
Oh, yes, I'm sorry. So Rich asked how basically this Jupyter Lite notebook is compiled. So I've got that in the demo here that I can actually pull up. Oh boy, where am I going? Yeah, so this is the GitHub repository. So if I click on this, This is just going to a personal public repository, but you can see at the top that it says that it was generated from Jupyter Lite Zeus Lite demo. If you click this Zeus Lite demo, this is the original template. And so what you can do is simply just duplicate the template. They show you how to do that. You have to do a couple of different configurations in the repository itself to be able to use GitHub Actions, which will interact with GitHub Pages. And so it deploys itself with GitHub Pages. And you can see that with the URL in that notebook. It's essentially just the name of my repository. You can also just use an original Jupyter Lite template. They also have their own, but I really liked this because it uses those CondaForge channels. And even though I can't get it to interact with the requests library, it's really nice to be able to get the latest copy of some of those libraries. If there's ever a demo that's like right after things are released, it's nice to be able to do that. And then when you make changes, so if I go back to my repository, you can see I kind of cleared out all of the other stuff. But you simply just add your notebook into the content folder that's already there or any other files. And then every time you make a commit, it runs several of these workflows and actions. So you can see it just titles them with the name of the commit. But if you click in here, they take about 1.5 minutes to run. And the build does all sorts of stuff to be able to set up the MicroMamba environment that actually installs from CondaForge, and then to be able to deploy that to GitHub Pages. So they've made it really painless to be able to do stuff. The only thing, of course, is that if you're making all these changes, you have to wait however long it takes to be able to see it. But yeah, this is a really great tool. I hope to use this in future demos.
Quick question on this, just to clarify the advantage of the Zeus Python, it's that you have access to a broader range of the Conda, and so like it's not that more limited subset of what's in
MicroPip, correct, yeah. So typically you would, if you wanted to install netcdf, you would call micropip.install. So that's an actual Python library, and it pulls from a Jupyter Lite repository of all of these libraries that are known to work with it or optimized to work with it.
And it's just ready to, and I guess the other advantage is it's ready to go.
Yep.
For users.
And that low-level virtual machine, that's what it uses to interact with CondaForge, and it is actually compiled in there. If you went in there and checked the X-ray versions, it's the latest version. You can see that it uses Python 3.13, the latest version of it. So, and with that Anaconda setup that's in there, if I can show that really quickly, this is where you set up those libraries that you want. So you don't do the build environment. The build environment is the Zeus kernel, but the environment YAML contains all of those custom dependencies in there. It looks just like any other Conda YAML, but you could see it's got CondaForge, and then mscripten has its own channel as well. So, and then I just specify netcdf4, and that's the latest version of it in there. So, you know.
Yes, there's a question in the chat.
Yes.
From Celia O, who asks, you touched on OpenMF dataset before.
Yeah.
How close or soon is data tree to getting a multi-file function?
I don't have an answer for that. Celia in there, well, actually, I guess I don't have to restate it because it's in Zoom. But I don't have an answer to that, but one of the benefits to these open source collaborations is that if the impetus is there, you can certainly collaborate on it. The X-Array core devs have a really extensive library that you can contribute to. Like I said, I'm not sure when that's coming, but I would imagine it'll probably come someday. And for now, for the implementation that this was used for, just opening up the one file at a time is sufficient.
That was going to be kind of another question I had about not just the multi-file, but you said also it doesn't do remote file access. So if you had some sort of subsetting service for people that you already, or a custom library for your data set, it's probably best to stick with that.
Pretty much.
It would be for local, you download your netcdf and you kind of want to exploit it.
Exactly. With the cross-origin resource sharing stuff and with Earth Data Login, you've got one big problem of just getting through the cores first. making sure that it's secure. There's a reason that that exists. And then with Earth Data Login as well, sometimes it plays nice or not too nice depending on where it's coming from. You can imagine that most tools might see a browser making all these sorts of requests without any sort of way to get through that resource sharing, and it'll pretty much reject it. But yeah, I originally wanted to use this for an OpenDAP demo a few years ago, and it was a little bit difficult to do that. So I would imagine that there's probably a way to, maybe in a future demo, there's probably a way to get those files in there through the GitHub action. And I don't know if there's a way to interact with GitHub Actions through a Python notebook, but maybe there is, and that might be the way to do it because that'll put it in there. I mean, you're not going to have that flexibility, and then it's down to if you own the repo or not, but that's something I'd love to try to figure out someday.
And another, can you,
I'm bringing you the mic.
oh, thank you.
Oh.
Yeah, my question was, can you go from like your basic, like, can you construct the data trees yourself? Like if you wanted to control your output of your NetCDF,
Yes.
so like you construct the data tree and then export, is that also a?
Yeah, so if you, you can use open groups and it will generate a dictionary. And from that dictionary, there's a function that will allow you to create a new data tree from that. So if you wanted to only extract one of those groups and stick that in its own NetCDF file, you can do that. Yeah, fortunately, that's how those are kind of structured within Xarray.
Just a quick clarification question. The remote access through a data tree, that does work, just not with Jupyter or does it not work at all?
It doesn't work with Jupyter all, but
without Jupyter does it work?
not really.
Okay.
You would have to use requests, download it, or put it in memory, and then use that to interact with it. So I can't put an HTTPS URL in there since it doesn't have that FS spec support.
Okay.
Yeah.
Kind of related to Jupyter, just kind of probing out like what's possible with that. Like for example, if I wanted to plot coastlines on the plot we made, because if I'm using like CardioPy to do that and it's pulling like the natural earth borders, because that's like a request over the internet, Jupyter won't do that.
I think it's all compiled in there manually when it builds. That's a good question though. I didn't try to use CardioPy in there. I believe that's all compiled though. So
Okay.
yeah, I'm kind of curious about that.
This is just sort of tangentially related, but since we're on this topic, I know that like the Holoviz, the Python Holoviz visualization packages, like if you look at their gallery, they all run in the browser too. And I know that they do connect to external data sources. So is that just like downloading data or something, or who knows, or?
I'm not too familiar with that tool, but with this, it uses WebAssembly. So essentially, any sort of browser microarchitecture that's widely supported, this kind of interacts with that, which allows you to use it on your phone, for example. But I'm not too sure about that library you mentioned. You said Holoviz?
Just the visualization suite.
Oh, okay.
Holoviz.
Yeah.
So this is Pyodide? Or no?
This is not Pyodide.
Okay.
Pyodide is what the original Jupyter Lite uses.
I see.
Yeah, this is Zeus.
I see.
Yeah.
Still don't see Rajat in the Zoom.
Yeah.
So we did plan on having one more presenter, but it seems like they might be having troubles. We'll hang out and see if they join in, but I mean, don't feel pressure to stay here if you'd like to have a conversation out in the hallway or something.
Yeah, I want to see if I can.
Question, maybe? A hand?
Yeah, really excited to see this capability. I've been testing on my phone.
Nice, yeah.
Do you want feedback?
Yeah, that was I would love to do some sort of field study or something like that.
Yeah.
It would be great to go out into the field and use this for, I don't know if you can use image recognition or stuff like that, but that would be really cool if it could interact with your phone hardware. I just don't know if it can do that.
Just initial feedback, I get really some flakiness in the different browsers that are on iOS.
Oh, that's interesting, okay.
Yeah, I got it to work in DuckDuckGo and Firefox after a couple tries, but like file not found error and restart the kernel. I'm just curious about how would you go about debugging things like that?
Well, that's the problem, is that you kind of have to be a web developer to be able to interact with that, because the way that it works is it's all kind of inside of Chrome or Firefox or whatever you're using, and you have to be familiar with those access frameworks. And a lot of those issues have to do with security, which is actually a good thing. I mean, you don't want one browser tab to listen to the other browser tab sometimes. And so I know with Chrome, with Chromium, for example, they've got lots of different security stuff in there. I'm not sure about DuckDuckGo or anything like that, or if you were to use it in an incognito tab with no extensions or anything like that. Extensions might even interact with it. I'm not entirely sure, but
Okay, so it's a complicated area.
it is. It's been in development for a few years, but it's really expanded. And so I didn't know about this Zeus Python capability until just kind of reading through their documentation. And that's great, because in the world that I live in, with Earth Data Login, some versions of certain libraries are not compatible. The NetCDFC library is a good example of that, and so I really like being able to pin a specific version from CondaForge. So otherwise, all the other functionality seems to be pretty consistent with vanilla Jupyter Lite or Pyodide. Not sure why I can't see the chat on here.
I had a question about the
Oh, here it is.
kind of inheritance of like the dimensions and stuff. So you have the data tree, which is now like native, right? And when you go down to it, it's a data set or a data array.
Those are arrays.
Those are data arrays.
Yeah.
Okay.
And it's like that because it's within the same file. But before, what you would have to basically do is open all of those individual groups as individual data sets and then concatenate them all together.
Data array
Or you would have to use NetCDF4 Python, manually extract them once you traverse through those groups. Yeah.
And for the control, and it sounds like your dimension control, you can control for each group and
Yes.
everything completely independently.
Yep.
Okay.
Yeah, and that's where all those assumptions come in. If you're working with a level 3 or 4 collection, you know that there is a time dimension in there that uses, NumPy, date time things. You know that there's latitudes and longitude points in there. But sometimes you can have level 2 HDF files that have dozens of different groups, all sorts of different tracks and all sorts of different ways of organizing those attributes. Yeah.
And so the dimension, the setup of the inheritance and all that kind of stuff is just coming from the metadata of the NetCDF that you're looking at, or is it somehow infer? Okay.
Yeah, so it'll inherit the attributes and the dimensions, but you'll notice that it didn't inherit the coordinates.
Right.
For the coordinates, it's kind of contained to its own group, but if you wanted to, for example, run a mean on all of those groups, it uses that root level dimension to be able to do that.
Okay.
So if it's not in the root level dimension, you do have to manually go into that group.
Okay. Can you edit is it easy to edit, to add, is it?
Oh, yeah,
So if
yeah.
there was a malform edit, NetCDF?
Yeah, and I mean, you can, the way that you interact with attributes with Xarray, it's much simpler. There's lots of different methods that I had in there for just being able to copy attributes. There's also, for NetCDF4, with Xarray, it's real easy to do that. Just to even create a new data set, it's simple to do that, so.
So we actually have our third speaker now.
Oh, fantastic,
So
great.
Rajat was able to come back. So,
Thanks for your questions.
yeah, thanks everybody. So Rajat, we're so glad you're able to join us back. So I'm going to stop sharing from the main room, and then you have a notebook link, it looks like in the chat. I have that copied over to our collaborative document for everyone in the meeting, and then you're good to share screen like whenever you're ready.
Great. Thanks, Keenan and Chris, and thank you for the opportunity to present. And I'm sorry I had to drop off. There were some technical issues, and I took some time in figuring that out. But yeah, I've shared the link to the working notebook in the chat. It is based on 4 parts. So 2 of those are kind of homework. So I am happy that we'll be able to cover it. A brief introduction about me. So I am Rajat. I'm a computer scientist working with NASA's impact team at Huntsville in University of Alabama in Huntsville. And I lead the data science part for MAP, which is a NASA ESA collaborative platform. And I also intended to share some presentation, but I think I'll just skip it for with the context of time. One word about MAP. So MAP is a collaborative platform which gives you access to cloud-hosted datasets and cloud-hosted processing in an interoperable and standardized way. And you can use it for most of the biomass research. Almost all the biomass datasets are hosted on the MAP Stack platform. There are some ESA datasets as well, which are hosted on ESA Stack platform. And right now there has been a lot of interoperability efforts which are going in for the science working groups and people who are working on it. So there are 4 parts to the MAP platform, and slowly it is also using the Veda platform, which is again NASA's platform for working with cloud-hosted datasets. I don't have much time left, it seems, so I'll directly go through the hands-on exercise. And this is based on some of our previous presentations at FOSS4G North America and other venues as well. And we have expanded it to showcase the benefits of cloud-optimized LiDAR data. So just a quick hand check, how many of us are already aware of cloud-hosted and cloud-optimized datasets?
You got probably like 80% of the room.
Awesome. Then we can cancel the talk, I guess. No worries. So yeah, the cloud optimized LiDAR datasets is standard, which I mean the standard is COPC, which stands for Cloud Optimized Point Cloud, and it is based on how we can leverage the cloud optimized techniques, which is basically coming from range request to get easy access and efficient access for datasets. And if you can follow that link, it's a binder link, so it will open up to a hub. Can I get a quick response if you're able to see the same hub which I'm seeing as of now?
Yeah, folks are able to open it. I know when I opened it, I got like a file not found error, but I was able to get to the notebook by like clicking into the folder icon on the side. And
Yeah,
that-
so
yeah, Tasha, so if you, Tasha said in the chat, file not found error, if you click on the folder icon and then click into the ESIP July folder, that
Yeah.
the notebook file that Rajat is showing is in there. So you should be able to just like navigate to it.
great. Thanks, Keenan. So yeah, Tasha, if you can click on the eSIP July 2025 folder, there is a notebook there. This is, okay, great. So this is based on the binder which is installed currently on Map Hub, which is a platform for working on collaborative processing environment. So what we are going to look into today is, I planned it in 4 parts. One is taking a last file and converting into COPC using Poodle. Poodle is an open source library which is an equivalent to GTAR, we can say, for point cloud datasets. It has a lot of functionalities. and we'll see how to use Poodle for converting LAS files, which is uh, the earlier standardized format for hosting LiDAR data and converting into COPSI. Then I planned some benchmarking experiments to see what is the processing time and what are the advantages we get from COPSI. But I'll recommend all of you to go back and try it out with open registry based URLs. And the biggest advantage which we can see with COPSI files or cloud optimized LiDAR data access is that you don't have to download a file. So the conventional approach where we used to download a very big data set, do the processing and then generate results, that can be replaced by directly reading cloud hosted files and then doing the processing. And then finally, we'll also look into some new tools coming from a team at DevSeed based on Lawnboard and Detailer, which allows you to visualize point cloud into Jupyter notebooks along with other data sets such as rasters or forest trails or any point data. So everything is based on this notebook, and let's jump right into it. So the first part is about creating an environment. We don't need to do it actually, because since this is a binder hosted, we have added the environment file, which you can see here at the root repository. And once we open this link, the environment gets settled in for us. We can see this here. So we'll be using, for the first part, we'll be using the Earth Access library. Okay, but before that, how do you want to do this? Like, should we go ahead and run each cell, or should we talk about it more? Keenan, sorry, you got to come up to the mic again to tell me the response.
You're asking if we should dig it. I think most people in the room are probably familiar with Earth access.
Okay.
So I
No, I
think,
meant, should I explain the notebook then? Will
yeah,
that be okay? Or do we?
I think we should put our focus on the notebook. What does everyone else in the room think? Yeah, everyone's nodding. Let's go ahead with the demo.
Okay, great. Thanks. So yeah, since this is okay. Perfect. So we'll create a data directory for this tutorial, and then for the first part where we are working on is the GLIT dataset, which is uh, a NASA dataset, and we are accessing it using Earth Access. So I'll not go into detail how to access that, but we can see the results. Very good. Okay. So yeah, we can see some of the results and collection which we are pulling in, and the data files are in .las file. So let's go ahead and download this file in our local dataset. So once it is downloaded, we can see it here. And we'll come back to this, but a brief introduction about PDAL or Poodle, as it's pronounced, as I said earlier. It's a library useful for working with point cloud datasets. They have a command line interface as well as a Poodle Python wrapper, which can be used for this. And it's very simple to use. We can just use Poodle info and provide the last file name. It also supports COPSI, the cloud optimized point cloud access. And once we do that, we can see that all the information about the last file which we just downloaded can be seen, including its metadata. So the bounding box and all the other options are available. Poodle provides pipelines to implement as a part of all the functionality or algorithms which are there. So these pipelines are implemented in a JSON-based format, or we can also do a pipeline construction, which is like just use the pipe operator, very smart of them. Just use the pipe operator and add more processing which you want to do. They have a lot of supported processing algorithms, and you can go and check the Poodle documentation. Uh, so we'll be using this for converting our last file, which we just now downloaded, and then converting it to a COPSI file. So we'll define the COPSI file name, just increasing the font size. We'll define the COPSI file name here and we'll run the pipeline for reading it and just writing it again as a COPSI file, which is cloud optimized point cloud. So we can see these are the number of points which we did, which are there in the file which we are working on. And now let's see the validation if we have downloaded it or not. So first thing, what we can see is there is a direct compression in terms of size of the file. Uh, the COPSI file is somewhere around 19 megabytes, but the last file is 66 megabytes. And this is this is not actually the main advantage of using any cloud optimized dataset, as I mentioned. But yeah, we get to get a, because in the COPSI domain, while we are working on it, we'll not even download the file. We will directly access it from the cloud. So that's the main idea there. And let's check if the downloaded file is actually a cloud optimized point cloud file or not. So if you use this pipe and then metadata for readers.copsy, it will give us a parameter as true. So basically, if there is a correctly generated COPSI file, we will see that in the file metadata. Any questions up till here?
None from the room. I don't know if you can hear me.
Okay, yeah, I'll go ahead with the second part. So second part, I wanted to have a benchmarking experiment where we can actually see how much time it takes in a LAS-based workflow as compared to a COPSI or cloud optimized based workflow for LiDAR analytics and processing. So in this case, what we are doing is we are taking two different files. One is in LAS format, and both of these are hosted on NASA map stack, the stack catalog for NASA map datasets. And then define a bounding box and try to get the overall processing timeline, which includes downloading a file as well as processing it. And the same processing algorithm we will be using with COPSI, which ideally should not download any file and directly access it and do the processing. So the take home results from here will be the implementation of how we do it, because since we are doing it only for one file, we might not find a lot of difference. As we can see here, like when we are working on this, we need to download a file. It will download a file. This workflow will download a file in our local directory, and the total download plus processing time is somewhere around 4.11 seconds. On the contrary, if we use a COPSI-based workflow, it is somewhere around 4.17 seconds, and the number of points processed are more. As I said, for one or two files, we might not be able to see a very stark difference, but we need to look after for a very big archive or large data archive to understand this. So later on, I recommend you all to go through these experiments and try for a big data set and other examples. So here I'm just showing some comparison and you can have a look at it later. Then there is one more benchmarking experiment which we tried for generating canopy height models based on any of the LiDAR datasets. And same, we are taking one LiDAR LAS file formatted file. And then another one is the COPSI file, which is not downloading anything, it is directly accessing and generating the CHM. So for generating any CHM or canopy height model generation pipeline, we can use Poodle like this. We can define a pipeline. First of all, we will read the LAS file. Then we will crop it based on the bounding box we want to do the processing. And then we will apply the filters which are required for generating CHM. In this case, when we are using the conventional LAS format, we need to download the entire file and then crop it. But when we will be working with COPSI, we can directly provide the crop bounding box and there is no need to download it, as I've been mentioning. So in this case, again, the difference is not too stark as of now, which we are seeing currently. But in fact, in this workflow, the COPC got more processing time as compared to last. But we all know that when we are working on a big or large data archives, this differences makes a lot of difference. I'll quickly jump to the last part, which is interactive visualization, because the benchmarking experiments were just as a homework for all of you. But the interactive visualization part includes two tools, which is Lawnboard, which is a tool developed by DevSeed team for visualizing point clouds directly in the Jupyter notebooks. And we worked on it for the GeoTrees use case, which has a lot of data sets, and they want to usually visualize multiple modalities of LiDAR data, including rasters generated from LiDAR, the point cloud, and the other information or data sets as well, like field level campaigns as well. So in this use case, the science example if we have to work on is something like how can I visualize different parts or different formats of LiDAR data in a single Jupyter notebook for comparing the outputs from them. So to do that, Lawnboard has multiple layers which does this, like point cloud layer, polygon layer, bitmap layer, which can be used for visualizing these data sets. I'll go ahead and run this. So in this one, I'm using one file which is openly hosted on MapStack. It's on my workspace, and we can read the file. We will read the file and subset it based on the bounding box. So this part will take some time. It says could not read from MapOps workspace. Oops. Okay. Okay. Probably I know what is happening here. Anyways, so yeah, I think this MapOps workspace is currently not allowing me to read the file because of permission issues. Uh, so usually what we need to do is we need to provide um, yeah, never mind. So we need to provide a file which is openly accessible, and then we can do this. But I'm sorry, right now it is not working. So I'll just go through the notebook. It's already there, and I can provide any other link later on for you to work on. So we can get the array values or data values from a COPC file using pipeline.arrays. First of all, we'll need to run the pipeline, and the pipeline actually is reading the COPC file here and then cropping it with respect to a bounding box. And from that, we can get the original array values or data values. Now we'll use this data values and convert it into a geodata frame with the CRS information. And since we are planning to visualize it, we need to bring everything into a common CRS, and then that is why we are converting it to the WGS 84 coordinates. Yeah, deleting some of the columns, this is very simple to understand because we only need the XYZ points as of now for our visualization. And then this is the important part where we define how to use point cloud layer from the Lawnboard library. So Lawnboard is the tool which we'll be using for visualizing all these different modalities. And it has layers supported for visualizing the data set. Here we are saying that we'll be using a point cloud layer and getting the data from the geodata frame. Then we can add a style, and for raster information, we can provide t-tiler endpoints. We can take any of the AGB values and use t-tiler to host or access those styles. And finally, there is this BCI trails file. So BCI is a region in Panama. It stands for Barro Colorado Island. And it is a region which is widely used for biomass-based research. It's a hotspot. And people, scientists usually go there on forest trails to get field level measurements. So they will note their field level measurements and field trails. And these trails are also, we are planning to visualize it in our demo. So this is openly available dataset from Smithsonian Institute. We can read it using the GeoPandas and get the data frame. And then finally, we'll merge everything together in the map format. So when we do this, it looks like this. We can just add list of layers to the map, and whatever layers we add, it will be visualized. I'll show the final output once I go through this, but right now there seems to be like the issue in the first step. So I'm so sorry for that. And the final thing which we wanted to do is, and this is already available online. What you can do is once you have worked on your notebook, there is this service known as notebooksharing.space, which provides you a way to share your notebooks directly with your colleagues or your teammates. So you can just download the notebook, what you worked on, and upload it here. And it will create a permanent link for you to access and share with your network. And yeah, let me try to get that link for all of us. So this is one example which we worked on in the past, and as we can see, these are how the plots look like in the already existing interface. These are also interactive in nature. So, for example, yeah, we'll wait till the time it gets loaded. So, yeah, overall idea is that please go through this notebook later. I'll fix the issues which we are facing as of now, and thank you for patiently listening to me. If there are any questions, I can answer those questions. But yeah, and feel free to reach out to me later if you want to work with the map platform or any of the or the Veda platform to access map or Veda datasets.
Thank you very much, Rajat. That was a super interesting tutorial. Give him a round. And thank you
Thanks,
everybody for attending our session and persevering through the unending technical challenges that come with a hybrid meeting. I'm so glad we were able to bring all this together. Thank you for Chris for helping organize this as well. And I hope all of you have a great rest of the conference. See you around.
Thank you, everyone. Thanks, Keenan. Thanks, Chris.
Yeah, thank you, Rajat.